So the purpose of Ockam is to enable um, applications to trust data they receive from the network, right? So if they are receiving a message that informs the application about something, then they want to be able to trust that message and decide whether it is a trustworthy message or not. This message could be just, some information that is coming from somewhere else in the network on a distributed application, or it could be some kind of command to do something to a machine, or it could be a firmware update. It doesn't matter what kind of data. We want to be able to decide whether we should trust this information we've just received over the network. And we want this to be end to end, right? We want the receiver of the information or data to know that the sender of the data actually sent that information. So if you dig in a little bit, we care about, if Alice is sending messages to Bob, Bob cares about the integrity of the message, the confidentiality of the message, the availability of the message, the authentication of the message, and the authorization of the message. And let me dive in a little bit there. Integrity here meaning that if Alice sent the value 100, Bob in fact got 100, and Bob can convince himself that 100 was in fact sent. Confidentiality is that people in the middle must not have seen this data. Bob wants this guarantee. Availability is about if Alice sends Bob 5 messages, Bob is convinced that he got all 5 messages, right? So if someone in the middle just hides one of the values, that could trick Bob into doing something that shouldn't be done. So we want to make sure that every message that was sent is in fact received. And then there's authentication, which is that, okay, I've received this value 100, but how do I know that this value 100 actually came from Alice? It needs to contain some proof about the authenticity of the data. But to have authenticity of the data, I also need authentication of Alice itself, right? So, or herself, because I need to know. So to authenticate the data, I will need, my message 100 will need to carry a identifier for Alice, right? So let's say it carries the name Alice. So I've got a message that says Alice sent you the value 100, but wait a minute, who's Alice? And like, how can I be sure that there aren't other Alices in the world that could have created the same message? Or someone else like Charlie could have created this message, right? How do I get a proof? So you're going to have to authenticate the sender and then authenticate the data to make sure that it actually came from that sender. So authentication has kind of these two meanings. And then of course, authorizations. If Alice is saying the temperature is 100 degrees Fahrenheit, is Alice actually authorized to inform me about temperature in my application or not? So all of these properties matter, right? And to enable trustful data in motion in distributed applications. And we want these guarantees end to end, regardless of the communication topology in my application. My application, Alice and Bob may be communicating to each other through a cloud service. So Alice's phone and Bob's phone are talking to each other through some cloud service, or Alice and Bob are two services in two different data centers and they're exchanging messages through some cloud service, or they're in different networks. Regardless of like all of these complexities and topology variations, we want to know at the application layer, we care about whether Alice sent this message or not, because Alice is the one I trust. If I don't have this end-to-end guarantee, then I can no longer really trust my data. And I'm not trusting Alice alone, then I'm trusting several parties in the middle. And we don't want to keep doing that. Like I said, these topologies could get arbitrarily complex. We might want to communicate through a cloud service, then stores data in Kafka, then the data gets consumed by Bob from Kafka. All of those like variations should be possible. But regardless of these complexities, the goal in Ockam is to simplify the ability to create this trusted communication down to a few lines of code, ideally these 2 lines of code. Step 1, establish a secure trusted channel. Step 2, send a message on that channel. That's what we want to enable, right? And there's some, this is the current API. There's some room to even make this even more succinct, and that we're working on. So this is the goal: get to, regardless of the complexity of the topology, be able to create these trusted channels and send messages through them. So the tool we need to do this is abstraction. We want to take these complex cryptography and security related protocols, and we want to hide their complexity as best as we can without taking away a application's flexibility as much as we can. There's a balance there. So the next few slides are about a couple of abstractions we had to create to make this possible. So the first thing we need is what's called an Ockam node. A Ockam node, this is a smallest program you can write in Rust to create an Ockam node. A Ockam node is a execution environment that can run lightweight, concurrent, stateful actors we call Ockam workers. So what are Ockam workers? Ockam workers, like I said, are lightweight, concurrent, stateful actors. They run in a node. They have an address, like a mailing address or an email address, but they have an address, like a string that represents the name, the address of that worker. They can maintain internal state. If they want, they can start new workers. They can receive messages from other workers and handle them. And these messages may come from workers on the same node or workers on a different node. And then, of course, they can send messages to other workers either on the same node or on a different node. So that's another useful abstraction. The value of this abstraction is that workers, because they are stateful and they can send each other messages, they're a really good tool to hide the complexity of a complex message-based protocol that when two workers are talking to each other. So if two workers are doing some cryptography and exchanging cryptographic messages, the end user doesn't need to be aware of all of that cryptography to use our simple create secure channel call. So workers enable this hiding of an encapsulation of a complex asynchronous messaging based protocol. This is how you create a worker. There's a little bit of boilerplate here, but this is the function to focus on. When a worker receives a message, this function is invoked called handle message. And inside the handle message function, excuse me, inside the handle message function, you can do something with that message. You can just print it and say, hey, where did this message come from? Or you can reply, because this is an echoer worker, you can reply to that message or echo back that same message. And to use a worker, this is what our main program, our main Ockam node code looks like. So the first step we do here is we start a worker. We take that echoer we wrote in the previous slide, and we say, hey, create a worker called echoer with address echoer in small letters. Then we send this echoer a message. So we say, hey, echoer, hello. And then, of course, the echoer is designed to reply to the same message with this reply with the same message. So we then wait to receive a reply from the echoer, and we say, hey, I'm waiting. And when the reply comes back, I just print the reply. So this is a very basic create a worker, send it a message, receive a reply. And you'll notice as you write Ockam programs, you don't actually typically have to create workers because we've created a bunch of them for you that do useful things. But it is a really useful abstraction and building block because it allows us to hide a lot of the protocol complexity. Okay, so the next abstract tool or protocol that we had to create was this idea of application layer routing. And it's a building block. It's a building block to hide the complexity of the underlying communication protocol, regardless of the topology of communication, right? So the Ockam routing message looks kind of like this, or looks exactly like this. It's a data structure. It has a version number, a onward route, which is a list of addresses, a return route, which is also a list of addresses, and then some payload that this message is carrying. This can be some arbitrary value, in our case, hello. This structure, when it travels over the wire, turns into a binary encoding, which we've put a lot of thought into how we can keep that compact, because we want to support lots of different communication protocols under this routing protocol. Okay, so this is what an Ockam routing message looks like. And so when you write this line that says send to the address echoer a message hello, this is what happens. Our main node program gets the default address app, and our echoer is that address echoer. So the app is the yellow circle with address app, and the echoer is the green circle with the address echoer. And on the top left there, we see the actual message that is created. So the app creates this message where the onward route is the address that we're sending the message to, echoer, and the return route is the sender's address, the app's own address. This message then arrives at the echoer, and the echoer, to reply it, basically takes the return route, makes that the onward route, because that's the address back, and then adds its own address as return route. So we get a reply back, right? This works. But we can take this a step further. This first value in the send function is actually a route, and it can have any number of addresses in it. It's a list of addresses that will become the onward route of our outgoing message. So in this example, here's what happens to the messages. In this case, we now have a worker in the middle called H1. So now, if you start from top left and look at the messages, the onward route initially is H1 echoer. This is exactly what we provided, right, to the send function. And then it reaches the H1 hop. It does something to the onward route. It does something else to the return route. We'll look at what in a second. Then the message arrives at the echoer, which again does something to the onward route, does something else to the return route, and the message then travels back to the app. So, and you can kind of go crazy with this and have any number of hops. In this example, I have 3 hops before a message goes to the echoer. But you get the idea, right? This is a general routing protocol where an onward route could be any number of hops before reaching the destination, and a return route is built along the path. And this is how this works. So when you send a message, the sender needs to know the route to the destination and makes that route the onward route of a new message. And it makes its own address the return route of the new message. The 3 little pictures are 3 cases we looked at earlier. If I'm sending just a message directly to a echoer, if I'm sending it via 1 hop, or if I'm sending it via n hops. This is the message I create. I know the onward route, and I insert my own address in the return route. So that's the sender. The hop in the middle, the forwarder, does these 2 things. It removes its own address from the beginning of the onward route, and it adds its own address to the beginning of the return route. This is what all the forwarders do in the middle. And then if you have someone who wants to reply, a replier makes the return route of the incoming message the onward route of the outgoing message, and it makes its own address the return route of the new message. So it's a protocol with a few, let's say 6 rules, but as long as we follow these 6 rules, we get a very flexible system to route messages around. And this is where transports come into play. So a transport is a plugin, a add-on to the Ockam routing protocol. It knows about the Ockam routing protocol and it moves messages between machines, right? So far, all the examples we looked at were moving messages between workers on the same node, the same program. But if we want to move messages across machines or across programs, we need a transport. And sending a message along a transport looks exactly like sending a message to a local worker, except you have to specify a slightly different address. So in this case, I'm saying, hey, the first hop in my route is a TCP address to localhost port 4000. The second hop is echoer on that node that is listening on localhost port 4000. So now I send the message and it works just like it worked before, except these transport add-ons know, the TCP transport add-on knows how to send this message over TCP and honor Ockam routing addresses and routes. So this works. Similarly, this also works, where you can have two TCP routes, where the first hop is a program listening on port 3000. The second hop is a program listening on port 4000. An interesting thing to note here is that it doesn't matter whether the sender established the TCP connection or the receiver established the TCP connection. The underlying TCP connection can be in any direction because TCP is a bidirectional protocol. The data flow can be in either direction and it still works. But if you have a different protocol which doesn't have a notion of a connection like UDP, then the transport has to handle that difference. But these are differences that are isolated to the underlying transport implementation. We could have just as easily written a route that was first hop is a UDP connection, the second hop is a TCP connection. And as long as those transport add-ons are turned on in a node, it would just work. The first hop could be a Bluetooth connection. The second hop could be a TCP connection. The third hop could be a stream that stores data in Kafka. The fourth hop could be another TCP connection. Doesn't matter, it would all still work. So this is where I want to introduce another useful building block abstraction, which is this idea of inlet. So an inlet turns raw data into a Ockam routing message. So that green box, inlet, takes a raw HTTP packet and turns it into a message that looks like this. A outlet, that second green little arrow shape, takes a Ockam routing message that looks like this and turns it back into a raw message, the HTTP packet in this case. So what we're doing here is there's a node running that knows how to do Ockam routing. We've got a vanilla HTTP server on one side, and we've got a vanilla HTTP client on the other side. And we're able to proxy data through or tunnel data through a Ockam node, where the HTTP client could be curl and the HTTP server could be, Nginx, have no clue about Ockam routing. They've just been written to, they're just your standard curl and Nginx, except when the HTTP client connects to the server, it's told, hey, don't connect to port 5000, which is the address of the Nginx server. It's instead told to connect to this inlet, which is at port 4001. And then what happens is data enters raw TCP data enters the inlet. It's turned into this data on the TCP stream is turned into a Ockam routing payload. It travels to the outlet, and where this Ockam routing, the rest of the Ockam routing message is thrown away, and the payload is turned into TCP stream data. And you can, of course, because Ockam routing, Ockam transports are just plugins, you can route inlets and outlets in all sorts of different transport protocols. Okay, so once we have this tool, what we can do is, so we've got a few building blocks now. We've got routing, we've got transports, and we've got these inlets and outlets. We can extend our communication where instead of having an inlet and outlet that was just passing through one node, we can have two Ockam nodes where the two nodes are connected by a transport connection, and the data is traveling through the inlet. It gets wrapped in a Ockam routing message, that little orange line, sent over, isn't sent directly to the outlet. In this new picture, it's sent over TCP to another node that is running the outlet program. It's unwrapped at that location, and then it's turned into a raw TCP message. And once again, the HTTP client, our curl program, and our Nginx program, the HTTP server, have no idea that there were these multiple hops in the middle. We can take this a step further, though. Remember, we're building a collection of reusable building blocks. Another useful building block is nesting of messages. So you can take an Ockam routing message and make it the payload of a different Ockam routing message. And this is very useful for running complex protocols. So one such complex protocol we have in our system is called a secure channel. A secure channel has an initiator, it has a responder. So you can imagine that Alice is the initiator in a secure channel handshake, and Bob is a responder. They run a cryptographic protocol called an authenticated key exchange, which involves public key cryptography. There are 3 messages exchanged in that exchange. The result of that authenticated key exchange is a shared secret. And then they use what's called authenticated encryption to then encrypt all the data that is exchanged between the initiator and the responder. This is a really complex cryptographic protocol. If we were to take the state machine of this protocol and expose it to end users, that would be a very complex thing to handle. It'll be hundreds, if not thousands of lines of code, and applications would have to tackle that on their own. Secondly, this protocol provides a set of guarantees. Remember that the guarantees Bob wanted from the beginning of the deck? This protocol guarantees data integrity across between the initiator and the responder. It guarantees data authentication. It guarantees confidentiality, but it doesn't guarantee authorization. You need a different protocol to tackle authorization between Alice and Bob. But we can use this protocol to get a few of our guarantees, right? But the challenge is we want to get these guarantees between this, let's say this HTTP client and this HTTP server, but we don't want to have to write like a really complex state machine handling code. And this is where Ockam workers are helpful, because they can hide all of this state machine handling code. And Ockam routing is also really helpful, because Ockam routing messages can be tunneled inside other Ockam routing messages. So let's follow what happens inside this program, right? Let's start from the left and go all the way to the right. So a regular HTTP client curl creates a HTTP message and sends it over TCP. Instead of saying send it to port 5000, we've told it to send it to port 4001. And so it sends it over TCP to port 4001. Over there is an inlet. This inlet takes that HTTP data. Maybe it's actually helpful to. I want my pointer, sorry about that. Okay, so this HTTP client creates a raw TCP message with an HTTP request in it. It sends it over to this inlet. This inlet then takes the HTTP data from the TCP stream and turns it into a Ockam routing message. This little orange line is basically my way of representing that we've now got an Ockam routing message. This Ockam routing message is sent to a secure channel initiator. But to initiate the secure channel, there was a complex protocol already run between this initiator and this responder. And so before we could have even sent this message, we need to tackle this green big box, right? And this green pipe is essentially running the handshake over TCP. But to do this handshake, we still wrap it in Ockam routing messages. So the second orange line outside the green line, or the green pipe, is representing that the secure channel handshake was also done using Ockam routing. And it was done over a TCP transport, which is this gray line. Right? So the first green pipe was established. Once this green pipe is established, because Ockam routing messages can be tunneled through other Ockam routing messages, the secure channel is really taking one Ockam routing message and emitting a completely different Ockam routing message, which is nesting the first Ockam routing message. So it takes the first Ockam routing message, it encrypts it, and then it wraps it in a new Ockam routing message and sends it down this secure channel. The message is received here. Now over here, the secure channel responder decrypts the message, and it gets back a new Ockam routing message, right? The decrypted value that was coming from this inlet. It takes that decrypted value, hands it over to the outlet, and the outlet then removes just the payload of that Ockam routing message and sends it over HTTP just like it was a regular sends it over TCP just like it was a regular HTTP request. And so Nginx here doesn't know that all of this was in the path of that HTTP request. So what's the benefit of doing this, right? The benefit of doing this is that we were able to transparently add secure communication between this HTTP client and this HTTP server. And we did it through a very simple, the protocol isn't simple. All my explanation wasn't simple either, but we were able to do it in a way that looked simple to the end user, because to the end user, it just looked like this, right? All of that underlying work was done for us. But let's take it a step further. In this case, there was only a single TCP connection between this node and this node. But what if we wanted multiple hops? Remember, Ockam routing can handle multiple hops here in the middle. So what if we wanted multiple hops here in the middle? And turns out that's just as simple to do as far as the API looks. Inside it, the protocol does a lot of that same wrapping and unwrapping and delivers the data. But the end user code still kind of looks like this, except for the route value here and the route value here is changed. Everything else looks the same, right? The route to Bob is changed, and then the message I'm sending through the channel I have with Bob is changed. So we'll do this one more time because I know this is hard to follow, but we'll do this one more time to highlight a few other points. So data starts at this HTTP client, which has no idea it's talking to a Ockam inlet and not to a regular HTTP server. It hands over the message here. The HTTP packet is turned into a Ockam routing message over here inside this inlet. So you get this little orange line outside the blue HTTP packet. That message is handed over to the secure channel initiator. The secure channel initiator has already used Ockam routing to establish a secure channel over this multi-hop route. So let's go back to how that may have been established. To make that possible, we needed a underlying routing thing to happen. This outside orange line needed to work first. And so we established a TCP connection between this guy and this guy. We established a different TCP connection between this guy and this guy. And this forwarder address is a little bit special because this thing is behind a remote private network, and we wanted it to have a public address. We have another little protocol that sits here that says, hey, give me a forwarding address on this public cloud node. And so that little protocol delivers a forwarding address, which the secure channel initiator has pre-existing knowledge about. And so it is able, this initiator establishes a secure channel with this forwarder, but turns out the forwarder is just forwarding messages to this secure channel responder. And so we get a handshake that actually completes across these multiple multi-hop machines. And so now the secure channel, the big green line, has been established. And then through it goes the blue line, again, using Ockam routing messages. So it's wrapped in that orange line, and it works all the way through. So, and when it arrives here, so it starts here, it gets encrypted, it takes this complex path, arrives here, it gets decrypted, out comes the encrypted Ockam routing message from the inlet is turned into a decrypted Ockam routing message. It's handed over to the outlet, and the outlet then unwraps the payload and just hands over the HTTP packet to the server. So what is the end result of all of this, right? We have now gone from a 2-hop secure communication channel to a multi-hop secure communication channel. In this case, we've gone from a 1-hop secure communication channel to a 2-hop secure communication channel. And because Ockam routing works over n number of hops, we could have X number of hops in multiple different protocols sitting here between this inlet and outlet, and it would all just still work. So now let's, now that we dove into this really complex thing, let's step out a little bit. What is the value of all of this? The value of all of this is that we want to be able to establish these end-to-end trust relationships using 2 or 3 or 4, like a small number of lines of code. And how did we achieve it? We achieved it by using 4 building blocks. The first one was workers, because they allowed us to hide all of this complex protocol running. So when we say create secure channel, this channel is actually a worker, but all the protocol handling is hidden behind that call. And it isn't because it is a concurrent worker, it isn't a blocking call. You can create a secure channel and do other things while the secure channel is being established. So the first building block was workers. The second building block that we looked at was application layer routing. Application layer routing allowed us to describe end-to-end communication routes that are decoupled from the underlying transport layer connection topology. They're even decoupled from the fact that you might have caches and queues and load balancers and gateways, all sorts of underlying things that may be in your communication path. All of that is hidden as long as you can describe a route to Bob, and then describe a route to something that is running near Bob in this send message, right? So application layer routing allowed us to hide all of the complexity of communicating between Alice and Bob. And then transports were the third abstraction we looked at, and transports allowed us to plug in transports into the routing layer, right? So the routing layer can be adapted to a variety of transport layer communication protocols, and that's a very wide range from TCP, UDP, and other standard internet protocols to non-internet protocols that aren't IP-based, like Bluetooth or Zigbee or LoRaWAN, etc. All of those can be very simple Occam routing plugins, and the application code doesn't need to change. The application code is just still describing a route to Bob that can be discovered from some central data store if you want, or registry. So transports were the third abstraction, and the fourth tiny abstraction we looked at were inlets and outlets. And inlets and outlets are just transforms that transform raw transport data into Occam routing messages. And inlets do that in that direction, and outlets do it in the opposite direction, where they transform Occam routing messages into raw transport data. But when we took all of these building blocks, we were able to describe secure communication that has all of these properties, actually a subset of them so far. It doesn't have the authorization property, but it has all of these first four properties. And we were able to describe that communication in a couple of lines of code with some setup that I left out for the purpose of brevity. But you'll notice from our various getting started examples that all of this ends up being like 10 lines of code, 20 lines of code, regardless of the complexity of this communication. And then there's this last property, authorization, is all about some set of rules for trusting. And those rules for trusting are encapsulated in this idea of trust policies that we'll leave for future discussion. But the key takeaway here is that Occam includes a set of building blocks, nodes, workers, routing, secure channels, and transports, inlets, and outlets. And these building blocks allow us to describe really complex communication topologies with end-to-end trust guarantees in a few lines of code.